Let's talk about the invisible spark that powers pretty much everything. I mean, from the thoughts firing in your brain right now to the very device you're watching this on. Today, we're diving into the incredible subatomic world of the ion.
So let me start by asking you a question. What in the world connects the electrical signals in your brain with, say, the salt you sprinkle on your food? I mean, they seem like they're from completely different universes, don't they?
Well, believe it or not, the answer is just one simple word: ions. These tiny charged particles are the unsung heroes that connect our biology, basic chemistry, and just so much more.
Now, to really wrap our heads around what an ion even is, we first have to understand what almost every atom in the universe is trying to do. It's on a quest for stability. And that's really the key to this whole story.
So at its heart, an ion is just an atom that's no longer neutral. It's got an electrical charge now. And the secret to this whole transformation? It all comes down to one little particle, the electron.
But why does this even happen? I mean, atoms don't just randomly toss electrons around. It's all driven by this powerful need to be more stable. Think of it like a puzzle. Every atom has these outer shells for its electrons, and they just feel most complete, when those shells are perfectly full. By becoming an ion, an atom finally gets that full outer shell, and it can just chill out in a stable, lower energy state. It's a goal pretty much everything in nature is striving for.
Okay, so there are two main ways this can go down. First up, an atom can just give away one or more of its electrons. And since electrons carry a negative charge, getting rid of that negativity leaves the atom with more positive protons than negative electrons. And what's the result? A net positive charge.
And you guessed it, on the flip side, an atom can also take one or more electrons from another atom. By grabbing that extra negative charge, it suddenly has more electrons than protons, which gives it a net negative charge.
So let's meet our first type of ion. These are the atoms that give electrons away, the positively charged ions we call cations.
Having a little trouble remembering that cations are positive? Don't worry, I got a great little memory trick for you. Just think of a cat. Cats have paws. They are positive. It's kind of silly, I know, but trust me, it's a surprisingly effective way to keep it all straight.
All right, so let's break it down. Cations are positive because they've lost electrons. A perfect example is sodium. You see that little plus sign next to its symbol? That's our sign that it's a cation. And this is not just some abstract chemistry thing. These exact sodium ions are literally what allow your nerves to fire and carry signals all throughout your body.
Now time for the other side of the story. Let's meet the ions that are formed by taking electrons, the negatively charged ions known as anions.
And yep, there's an easy memory aid for this one too. The name anion practically tells you what it is. Just think a negative ion. See, it's built right into the word.
So anions are negative because they've gained electrons. A classic example here is chloride. Now, what do you think happens when a positive sodium cation gets near a negative chloride anion? Well, opposites attract. They form an ionic bond, creating sodium chloride, which you probably know a little better as common table salt.
Okay, so we've got our positive givers and our negative takers. But why does any of this really matter? I mean, who cares? Well, it matters because this simple exchange of electrons is honestly one of the most powerful and fundamental processes on the entire planet.
Just think about the impact. Ions form the bonds that create countless compounds. Like salt, they are the literal engine inside every single battery, driving the flow of charge that we call electricity. And, like we saw, they are absolutely essential for life itself, powering every single signal zipping through our nervous system.
So we've seen that at this tiny atomic level, the drive for stability is powerful enough to create these charged particles that literally run our world. Which kind of leaves us with one last thought. If atoms are doing this, what else in nature, from a river finding the easiest path down a mountain to a tree growing towards the sun, is also on a constant quest for a more stable state? Thanks for watching.